record this. Today is the 9th. We continue on in this chapter. What we're going to do today is look at what's called the total differential. Okay, the total differential. It used to be extremely important a long time ago, the total differential, because it could be used to approximate change in a function z of two variables. But nowadays, the need to approximate the change in a function is just not necessary, okay? We have calculators in computer algebra software, computer algebra systems that do exact changes, okay, instantaneously. So the need to approximate change is really just not needed nowadays. It used to be really important because it was tough to approximate change in certain functions. I mean, with a slide rule or a table of logs or something like that, that was difficult to do, and it was not very accurate. But now that's not necessary. But there is still one application of the total differential that's still used today, and that's what we're going to do. And this will be on your test too, as far as that goes. But before I do that, I'll take any questions you have in any homework. No questions at all? It was pointed out to me that one of the questions you do have in the homework, a partial derivative problem, is involving sinh, okay? And it's something that should be covered in Calc 2. You should know that the derivative of sinh, hyperbolic sine of u, the derivative of hyperbolic sine of u is what?
Cosine of hyperbolic cosine of u.
Yeah, du dx.
We didn't actually cover that. I just guessed on that one on the homework. That it was cosine of that.
Yeah, we did.
We never covered that.
We talked about it for like a second, but we didn't like do anything with it because they said
Really?
I think they said we would do it in Calc 3.
I remember you went over it.
Yeah, we did. It was on your test.
It might have been.
It,
I don't remember.
it was, Spence.
We didn't
Yes.
cover it at all.
Yeah, like I remember one class we talked about it for like a second. I know I have it on my calculator.
Is that right? Well, anyhow, let me tell you this. The derivative of sinh u, here, if y equals hyperbolic sine of u is a function of x, the derivative is cosh, hyperbolic cosine of u, du dx, and if y is cosh u, the derivative is sinh u du dx. Now, what happens here is interesting. These hyperbolic, here, the definition, you should know the definition actually. Hyperbolic sine of x is equal to e to the x minus e to the opposite of x over 2. And the hyperbolic cosine of x, cosh x, is e to the x plus e to the opposite of x over 2. There's certain problems that are solved with these functions, okay? They share properties like trig properties, but not always. For example, the derivative of sinh is cosh. That's just like the derivative of sine is cosine, okay? Same thing. But the derivative of cosh is not the opposite of sinh, it's the sinh. So sometimes the properties are the same, identical to the trig properties, but sometimes they're off by a sign, S-I-G-N, plus or minus, okay? The best application of these two is the cosh function for whose graph looks like this. Just go over this quickly here. Graph looks like this here. This is the cosh. It looks like a parabola, but it's not. It doesn't have the same properties of a parabola, being a combination of these exponential functions. But the application is, if you take two poles and string a wire between the two poles, that wire is not in the form of a parabola, it's in the form of what's called a catenary. And the catenary is a form of cosh, hyperbolic cosine. So that's an important thing. It's a fundamental kind of thing. Just put a wire between two poles, it'll be in the form of a catenary or hyperbolic cosine. So those kinds of problems are solved with these hyperbolic cosine and sine. Now, there are others too. We don't really get into them. I don't think we're going to mention these again this semester. But I did notice, it was, like I said, pointed out to me that in the homework that you have some partial derivatives involving sinh and cosh. Okay? All right, so just to go over that. Any questions at all? Okay, fine, let's go on. Total differential. Let's talk about the total differential. Given z is a function of x and y, the total differential dz is equal to the partial derivative of z with respect to x dx plus the partial derivative of z with respect to y dy. That's the total differential. And it's used to approximate change in z. Like I mentioned, this has been deprecated, to borrow a computer science term, over the last few years. It's just not necessary to approximate things, but you can use this to approximate the change in some z function by taking the partial of z with respect to x times the change in x plus partial of z with respect to y times the change in y. And hopefully this will make some sense. After all, if we want to approximate the change in z, if we know how fast the function's changing in the x direction times the amount of change in the x direction plus how fast it's changing in the y direction times the amount of change in the y direction, that'll give us a good approximation for the change in the function. How fast it's changing times the amount plus how fast it's changing in that direction times the amount will give us the total change in the function. It's a good approximation. Well, we won't be using it for that. We will be using it for this, however. Suppose you have to measure the dimensions of this room. Okay? Well, inherent in measuring anything is error. There's error in measurement. Let's suppose we were to measure this room. We needed the surface area of this room for some reason. And we measured the room, and you had, say, 1% error in measuring the length, the width, and the height, each of those three dimensions. What kind of error could we expect in the calculated volume of that room? Or the surface area of that room? Did I say surface area first? I think I said surface area. Let's do surface area. What kind of error could we expect in the surface area of that room? So we got error in each of the individual measurements. We use the measurements that we did, and we calculate a surface area. Well, there's got to be error in the surface area. How much error is there? That error is called a propagated error. Okay? And here's what we're going to do. We're going to find that propagated error, and what we're also going to do, more importantly, is find the percent relative error, okay, in using those length, width, and height to calculate the surface area. We're going to use the propagated error. And how do we use the propagated error? How do we find it? By using the total differential. Okay? So let's take a look. Everybody all set on this? Here's what we're doing. Okay? So we've got a rectangular solid. Okay. It's got length. It's got width. Right angles here. It's got height. And what we want to do is calculate, and let's suppose we have 1% error in each of these measurements, okay? We have 1% error. Given that, what's the error? Here's what we want to do. Find propagated error in the calculated surface area And we also want to find the percent relative error in that calculated surface area, okay? That's what we want to do, all right? So, let's figure it out. S, surface area, is equal to, well, what's the surface area of a rectangular solid? Where were we at there?
Sorry, what did you ask? 2 times width times length.
Yeah, length times width. We want the surface area. Plus
2 times height times width.
width times height.
And 2 times length times height.
Okay, fine. Good deal. That's the surface area of this rectangular solid. Okay? Well, each of those measurements, the length, the width, and the height, have error. Okay? A 1% error. Here's what we're going to do. We're going to find the error and approximate it with the total differential of S. Now, we have S as a function of 3 variables. It doesn't matter, okay? We just take the definition that I gave you and add on another variable. In other words, what we're going to do is find the partial of S with respect to L, okay, times dl, partial of S with respect to H dH. This is the total differential now. Partial of S with respect to W dW. And we're going to find that, okay, by doing the following. Take the partial derivative of S with respect to L. Now, what's the partial of this with respect to L? Partial of S with respect to L is going to be
2W.
Plus 2H.
that away. dl plus partial of S with respect to H. Yeah, you're a little too slow. All right. I'm sorry. Plus partial of S with respect to W. Okay. Okay. Yeah, and think about it. It does. Hopefully, it makes some sense. We've got a calculated surface area, and we want to find the error. And the error is going to be how fast S changes with respect to L times the change in L, how fast it changes with respect to H times the change in H, and how fast it changes with respect to W times the change in W. These changes here are the errors. So, here's what we have. 2W plus 2H dl with a 1% error. What we have here is plus or minus 0.01 L. Okay? You guys still okay? Just hang in there. Hang in there. What'd you do? Work all night, Dan, or what?
No, I did work, and I wasn't supposed to, but I did work.
Did you? Yeah. You guys work hard. You do. You all work hard. DH is the change in H. That's the error in H. That's a plus or minus 1%. H. And DW? Hey, DW. What does DW stand for?
My initials.
It does, Dan. You know what? I wasn't even thinking about that, but there you go. You know what I was thinking of?
Don't worry.
Don't worry. That would be another good one. What's that?
No, not that.
Oh, I was thinking about Arthur.
Arthur.
Arthur. DW is sister. Dora Winifred. Is that it? Arthur, you know Arthur? Yeah. Dora Winifred, right?
Sure.
Think. I haven't seen Arthur in a long, long time, like 15 years, but yeah, Dora Winifred. DW. Yeah. The brain, the brain was there, and Mr. R.Burns, the science teacher guy. All right, but anyhow. All right. Okay, never mind.
No,
Okay.
it's just going to get worse and worse as you keep teaching. these things are going to become more irrelevant.
Yeah. That's what happens. Okay, plus or minus 0.01 W. All right, here's what we're going to have to do. Boy, this is a nasty problem. It's turning into a nasty one. All right, so let's see what we have here. Okay, I'm going to take this and we're going to simplify this thing to the best of our ability here. Okay, I'm going to take this away. Everybody else set? Okay. So here's what we have. ds, the error in S, is equal to. Well, here's what I have. I've got a 0.01 in each of those three terms that I'm going to take out front. Okay, I'm going to take a 0.01 out of each of those three terms. Now, in the first term, that leaves me with an L times that 2W plus 2H. So here's what I'm going to do. I'm going to multiply through by L and get, in the first one, 2LW plus 2LH. That's in the first one. Multiply through by the L. Plus, in the second one, I took the 0.01 out front, and now I'm going to multiply each of those by H. And I'm going to get a 2WH plus a 2LH plus. In the last one, I'm going to multiply through by W. And I'm going to have a 2LW plus a 2WH. Okay? Everybody okay with this? Okay. Now, let's combine all these. Let's see. I have 2 LWs and 2 more LWs. I have 4 LWs. Plus, I have 2 LHs, 2 more LHs. I have 4 LHs. Plus, I have 2 WHs plus 2 more. I have 4 of those guys as well. Okay. Now, believe it or not, what I want to factor out front from what's inside the square brackets is not a 4. What I want to factor out front is a 2. Okay? So I'm going to have this. Why would I want to do such a thing?
Then you're left with your original.
That is correcto. So I have this. This is the original surface area S.
Why is it, if you factor out the 2, why is it 0.02?
Because 2 times 0.01 is 0.02. No problem. DW, that's it. You got the DW. Wow. Okay, that's pretty cool. All right, but anyhow, what does this tell us? This tells us the following. That the error, propagated error, is 2%. Okay? That's a 2% error. It's plus or minus 0.02 times the calculated surface area. That's the propagated error, 2%. I did more than that. It's the percent relative error, okay? Is 2%. Because how do you find percent relative error? Okay, take the calculated error divided by the calculated surface area, okay, and multiply by 100%. Okay. The S's cancel. You get a plus or minus 2%, but the plus or minus is built into this. So I'll tell you what, let's take an absolute value. Okay, because you never say, the percent relative error is 2%. Okay? Implied in that is a plus or minus 2%. Okay? Which is kind of weird. It's not what I expected. I thought there would be a 3% error. But if you got a 1% error here, 1% error here, 1% error here, and calculating the surface area, you're only going to get a 2% error, which is kind of interesting.
Wouldn't they overlap at some point?
Yeah, that's a thing. Because it's surface area, you only multiply 2 at a time together. If we were doing volume, I'd be willing to bet we're going to get a 3% error in calculating the volume. Let's do it, okay?
I think you might get even less.
What's that?
I think you're going to get less than 2%. I'm just going to throw that out there.
Really? You think so? If I do volume?
Yeah, let's try it.
All right, let's try it. Let's try it. Wait, what did Matt say? Whatever Matt says is going to be the truth.
Well, I was thinking it should increase because you're measuring more potential variables. So if the error comes from, did you get the length right? Did you get the width right? Did you get, so if you're doing it over the volume, we are doing it over the volume now, right?
We're going to do the volume right now.
So the error is going to have a bigger effect.
So you think it's going to be greater than 2%?
Yeah.
All right, so Dan says less than 2%. Somebody say exactly 2%? Spence, what do you say?
I'm feeling 3%.
What's that?
I said I'm feeling 3%.
3%? Anybody else want to get on the record here?
100%.
Huh? 100% error. 100% error. What is that?
Jordan says 0.
I did not say
Let's take a look. All right, let's do volume. Volume is equal to length, width, height. Okay? So, total differential, partial of V with respect to L, dl, partial of V with respect to W, dw, partial of V with respect to H, dh. That's equal to partial of V with respect to L is WH dl. Partial of V with respect to W, LH dW. Partial of V with respect to H, LW dH. Okay. So we have WH and we have a 1% error in L. We have LH and a 1% error in W. And these errors don't have to be same. We could vary the errors too, okay? But I chose 1% for some reason. LW. Okay. So what do we end up with? dV is equal to. Now, please note, I can take out, again, a plus or minus 0.01 out of each of these. And I'm going to get an LWH here plus an LWH here plus an LWH here. We have 3 LWHs. 3 comes out. LWH is equal to what? The volume. 3% error is what we have. The percent relative error, okay, is equal to plus or minus 0.03 V divided by V times 100%. I'm probably off the table here, am I? No, I'm still on there. Wow. And that's equal to a 3% error. Okay? And that's what we get, a 3% error. It's kind of interesting. If you're doing something that's square, like if we were doing volumes of cylinders or something like that, a pi r squared h, what do you think happens with the r squared? Suppose we had a 1% error on each of those measurements. What happens because it's r squared? What does that contribute to the calculated error in the volume? Because we're squaring the r. What's that?
Smaller.
You think smaller?
No.
Wouldn't it double it because we're doing the derivative?
Exactly what happens. It doubles the error contributed by the that radius. So what you would get there is twice the error, twice, and then you get 1 part error from the height. You get another 3% error because it would be twice from the radius and 1 from the height. And you could do it out. You could do it out. Yeah, you could certainly do it out. It's kind of it's interesting stuff. But that's propagated error.
Is that it's going to be on the homework from assigned pretty much these types of
Yeah, except web assignments may
Little,
tend to go overboard sometimes with these. But on the test, it's this kind of thing you're going to get. Okay, you're going to get something like this. We could do the cylinder one. Why don't you guys do the cylinder one? Go ahead. I met with a rousing. Yeah, why don't you do the cylinder? What the heck? Might as well do the cylinder one. Volume of a cylinder. We're counting the volume of a cylinder. Okay. Volume of a cylinder, pi r squared h. Okay. Pi r squared h. And let's say it's we'll go to 1% error again. Although you know what, it doesn't even have to be a relative error. You could do an absolute error in the measurements of plus or minus 0.1, 1/10 of an inch or 1/10 of a centimeter, as opposed to a percent error. But let's go with a 1% error.
You said volume, right?
I said the volume of a cylinder, pi r squared h.
1% error both in radius and in height.
Yes,
Okay.
yes, do that. Why don't you figure out the percent relative error in the calculated volume of that cylinder. Tomorrow we'll do some chain rules stuff. Then we get directional derivatives and gradients. But I think what I'm going to do is this. Here's what I'm going to do. Friday, I think I'm going to do help day. I'm going to be here on Friday. But you don't have to be here unless you have questions on homework, whatever. Okay. So if you have some questions on homework or anything like that, I'll be here on Friday to answer them. But if you don't have specific questions, you don't have to be here on Friday. Okay. Tomorrow I'm going to do the chain rules. We'll do these little chain rule things. It's kind of interesting. But after break, then we'll do the directional derivatives and gradients, which is the real stuff of this chapter. I hope what I said is true. I hope that's what it comes out to be. Is it coming out that way? Did you get it?
Not yet.
Oh, okay. Does it look like it's going to come out that way?
It looks like it should.
Okay, good.
Yeah, I got 3.
Spencer got it. That's it. It's a wrap.
I mean, I'm basing it being right off you saying it should be true.
I'm assuming you did the whole problem, Spencer, and there it is.
I did. I don't know if I did it right. No.
I'd be betting on you. You ever in touch with Allie at all?
No, isn't she in like
Iowa.
Iowa?
Yeah, she's in Iowa.
What's an Iowa? Talk to her.
What's in Iowa? College. I don't even know what college she's going to, though. But she's majoring in like agriculture, plant, something or other.
Yeah. Because I know, like, my friend went to a school, like, I think in Illinois or something out there.
Where is it?
Wells Holman. I think it's out there somewhere.
Out there somewhere, yeah.
It's a really good engineering school.
No kidding.
Yeah.
Oh, that's interesting. It could, maybe she's going to University of or Iowa State.
I haven't talked to her in like almost a year.
Oh, really?
Yeah. I don't know.
You know, my daughter was talking to her on the phone over the intersection in Park Place. I think Allie came home.
Oh, no.
I don't know. I can't remember now. But I said to my daughter, let me talk to her about, I want to talk to her about Spencer. But then my daughter said, oh, Allie's got to go. So I didn't get a chance. But anyhow.
She should stop in and say hi.
What's that?
She should stop in and say hi.
I'm going to tell her. I'm going to, if I get to talk to her.
And then
We'll see.
put the R.
So you're there like all the time or what?
I'm there Wednesday and then all weekend, like Friday, Saturday.
Oh, okay.
I think I was better.
Actually, you guys don't still have that special on the bird seed that I had from the fall, right? There was a special deal that I had to pre-order is what I did.
The black oil.
Yeah, black oil sunflower seeds and the like a case of suet and there was something else there too.
Yeah.
Fruit and nut mix or something like that. I have to come in one of these days because that stuff is just about gone.
I think the black oil is still up there.
Is that? I'll have to
I
check
think
it
it's
out.
like 21 or 24.
All right, check it out.
I thought I messed it up, but then I fixed it.
So what'd you get?
I got plus or minus 3%.
3%. All right, good. That's what I thought it would be. Let's do it. You guys ready? Volume. Pi r squared h. Total differential, partial of v with respect to r dr. Partial of v with respect to h dh. Okay. Partial of v with respect to r2 pi r h dr, a plus or minus 1%. Partial of v with respect to h, pi r squared, and then a plus or minus 1% of h. So what happens here is we get a 2 pi r squared h, a plus or minus point. I could have taken the plus or minus 0.01 out, but I didn't. Shoot. All right, pi r squared h. Now I will take it out. And then I have 2 pi r squared h plus another pi r squared h, which gives me 3 pi r squared h. And then, and this is what your Dan just said, because of the r squared, we get an r2 coming out, which will double this amount here. And if you had something cubed, it would be, it'd be 3 times that thing squared. Yeah, it'd be 3 times the amount. It's true. And what do we get here? Plus or minus 0.03 times pi r squared h, which is the original volume. So the percent relative error, take this, divide by v, multiply by 100%, take the absolute value, is a 3% error. Okay. So 1% in each leads to a 3% calculated volume because of that square of the radius.
And we still use this. This is like the only application we still use this there.
Yeah, this is the only application, and you're going to have some, I'm going to give you on the test something just like this. Okay, that's what's going to be on the test. All right, so tomorrow we'll do some chain rule stuff. Friday we'll do, I'll take questions, and then spring break, and then we'll come back, and then we'll keep on going from there.